Good morning, everyone. Today, I will talk about a paper that is published in KDD last year. The paper named HAT, a Hierarchical Sequence Attention Framework for Inductive Set-of-Sets Embedding. So let's start, right? We are working with machine learning, and traditionally machine learnings deal with the data in the form of either the fixed dimensional vectors, for example, like images, when even though we have images of different sizes, right? But when we actually learn from the image, we rescale it, we crop it to a certain size, and then we learn a model. In this particular case, for example, if the image resized to 224 by 224. Another example is like text sentiment classification, for example. Then the text data is ordered in sequences. So we want to capture the orders of the symbols in the text. But it's not the case all the time. In some of the cases where the input data actually are sets. Here's one example. So this form of data is named point cloud data. So this form of data comes mainly from the 3D sensors, like kinetic sensor, or like the Face ID of iPhone, for example, or for example the LiDAR sensors on the autonomous car. This form of sensor, they have the camera to capture the 2D image, and then they have another depth camera to measure the depth from the point of the camera to the point in the space. So mainly the data represented as the point with the 3D coordinate x, y, z in the space and the value of the pixel. In this particular case, for example, so we also have the same task, like we want to do the classification or regression as normally what we do in machine learning. In some other cases, the data even come from the hierarchical structure, like set of sets. If we think about it, this is one of the example when we have the graph, but inside the graph we have subgraph. So we already have the subcluster of graph. So we want to make use of that kind of structure to actually, for example, in this particular case, we want to predict the subgraph hyperlink predictions. Let's say like coronavirus, right? We want to predict the hyperlink between different clusters, for example. So in this case, we have set of sets form of the data. Before I go through the main paper that I want to present, I want to walk you through one of the paper that published in NeoRIPS 2017. The paper named Deep Sets, and this is a foundation that a lot of people now working on the set representation learning based on. So the main contribution of the papers come from how they actually represent the data and how they actually derive the architectures and the theory that we can actually learn from the set data. So the first important thing I want to talk about is that the problem definition. So we also perform normal machine learning tasks like classification or regression, but the data now is a set. So we don't care about the order of the data. And the number of elements of one particular example can vary. So it can be 3, 4, 5 that actually comes in a different orders. So the objective is to learn a function fx that operating on the set and output the result is same as the classification or regression. And this is one of the example. Let's say we have the images of a digit and we want to learn a function, let's say a sum function. So we input a 3 image of a digit, then we can actually output the result there. This is one of the example. So this actually the number of the element can vary, and the order of the images here can actually permutate, and then we still have the same output. That is the goal for our model. So in order to do so, they derive this characteristic of the functions that operate on the set data. So there are two main properties that they want to capture when they learn a function. The first one is the permutation invariant. So permutation invariant means that when we permutate the input, the output doesn't change. So this is the definition. So pi is a permutation. So you permutate the input x, but you still have the same output. This is one example, right, as I given earlier. So when you permutate the input, the image, you still have the same output. The second property is permutation equivalent. So this one, the definition is that when you permutate the input, the output permutate in the same way. So if you given one particular permutation of the input x, you get the same permutation of the output. One of the example that I can come up is, for example, like this. Given image of 3 people, then you predict where they come from. So here is the image of our postdocs, right? So when you permutate the input, then you have the same permutation of the output. So that is the two main properties that we want to capture when you learn a function that operates on the set data. Okay, so in order to do so, they provide some theory and some analysis and proof of the architectures that actually can capture those properties. So for the first one, the permutation invariant, the function actually gonna be factorized in this form. So the main part that we actually notice is the sum function. So the input x, right? The x is the set. So inside this set we have the multiple element x, and this 5 here is a transformation. It can be nonlinear transformation, but for the intermediate representation of x, you have the form of the sum function of that transformation, and then you have another transformation and output f x. So this is the form of the function that can capture this property, the permutation invariant. So the proof is provided in the paper, but intuitively it's quite easy, right? Because we know that the sum operation has the commutative properties, right? So it doesn't matter the order. The sum gonna give you the same output. So not only the sum, but some other operation that we might be familiar with, like max pooling, some kind of pooling function that we normally do in the neural networks, also have this property, permutation invariant. So this is one of the basic one when they architecture, when they build on top of this property. When you have the x, it's a set of x, you have multiple elements, and then you have the phi transformation here, then you have the intermediate representations, and then you sum the representations, and then you actually output the prediction that you want to learn. The second property is the permutation equivalent. So in order to achieve that property, we need to learn a function fx parameterized by the theta here. And the theta matrix comes in the form of this. So what it says is actually, let's say the matrix theta is in the size of 3 by 3, then the form of the matrix is going to be like this. So for all the diagonal of that matrix is the lambda plus gamma. For all the off-diagonal elements, it's going to be gammas. So you're going to see, I mean, it's a little bit hard to imagine here, but let's see if you can contrast when we see this visualization. So let's say we have 3 elements at the input. So given this transformation matrix, you're going to get this output. So this edge represents the weights, right? So the blue one represents the diagonal, which is the lambda plus gamma, whereas the all the off-diagonal elements is gamma. So then it's give the yellow edges here. So when you permutate the input, you get the same permutation of the output. Whereas this one is normally like the normal matrix transformation when you have the arbitrary weight, which is like it doesn't preserve the permutations equivalent. When you permutate the input, you're gonna get a very different output because the weights are different, so they are not tied together. So given the previous architecture, this architecture, they actually, so this is the illustration of how this works. It's actually, you have the transformation of all the elements here. Then this one is actually the representation of this element plus the weighted sum of the other elements. So you can actually think of other elements as a context. And those contexts have the same weight. And plus with the elements of the that current position, then you get the representation of that elements. And this is the illustrations. We can discuss this further later, but for now, these are the two main properties of the function that we want to operate on the set data. So now we come to the main paper today. The name is HATS, and this paper is designed to work with set of set data. So first I want to give this is a paper, they give the definition of the what's so-called the inductive set of set embeddings. So the objective is to actually learn a function f, and this function actually taking the tensor A, 3D tensor, n by m by d. So n is the number of set, and m is the number of element in its set. D is the d-dimensional representation of each element. So they can be one or they can be high dimensional. So in contrast to deep sets, right, you don't have this dimension. When you only have one set, then you have the m is the number of elements, and then d is the representations of the each of the element in the set. So the output is that what you want to learn is actually you want to learn the function f that permutation invariant to the first is the permutation at the set level, and also invariant to the permutation in the at the element level in each of the set. So one question arises, right? Why don't we merge all the elements and just use deep set to learn, right? Why do we bother to learn actually like set of set, and then it's make things more complicated? So the answer is cannot lie. We need to preserve the actually the hierarchical structure of set. So in some of the scenario, we actually want to make use of that hierarchical structure, then we can actually learn a better representations of the data. In the paper, they actually give the proposition and give the proof that for given set of set embeddings, under any encoding scheme that turn the set of set data into a set, so you actually there is the representation of the set of set that cannot be represented by learning directly from the encoded plain set. Essentially, I mean, in other words, it's actually we will lose information when transforming set of set to plain set under any encoding scheme. So the basic idea is that we actually lose information when the main information comes from the structure of the data. Another theorem that they given in the paper is actually to guarantee the permutation invariant properties of the model. This actually generalized the result from deep set paper, so from set to set of set. So actually from deep set, we already have the function that preserve the permutation invariant properties that have this form. So factorized in the form of the sum of the transformation of each element. So when you go to the 3D, when you have multiple sets, then this is what you get. And if you set n equal to 1, then you're going to come back to this one. So it's a generalized proof of the deep set paper. So this is the architecture that they propose in the paper. So for those who have been working with, for example, text classification, you might have come across these architectures. So this actually the paper, the hierarchical attention network that proposed in the NAACL 2016, and it actually exploit the structure of the hierarchical structure inside documents from the words, then from the sentence level, and then the document level. So this paper actually based on this hierarchical idea from this paper. And you can also find the same kind of architecture in our paper, VistaNet, presented in KDD-19 last year. That's it, 5 seconds for self-advertising. Okay, so given these architectures, this is how they learn. So they actually based on stochastic optimization, but it's the same like what we are learning with all the neural nets. But the main idea is that they have these two permutation layers. So at this layer is the elements level. Then they permutate the order of the elements, and then in this particular level they permutate the order of the sets. So for each of the batch, we permutate the set first, and then we go into each set, and then we permutate the element inside each of the set. So during learning the stochastic optimization process, then in the end, the objective is try to capture the permutation invariant inside the data. During the inference, they're gonna use the multi-category sampling. So they're gonna sample, and then they're gonna approximate the representations of the set. For experiments of this paper, they conduct experiment on 4 different tasks. The first one is the simple arithmetic task, when they actually try to do 5 different arithmetic operations. The first one, binary, is this one they try to find the intersection of the set. So given the multiple sets, then the output is the intersection of those multiple sets, the elements inside those multiple sets. And then since they do the sum, so they sum all the elements in the intersection. So after they find the intersection, then you output the sum of that element in that intersection. And this same, they sum all elements in the union. So union is another operation that operates on the sets, right? So you find the union of all the sets, and then you do the sum of all the elements inside the set. They also conduct experiment on the other 2 operations, like unique count. So they find all the unique elements across all the sets, and they count how many unique elements. And then another task is that they sum on those unique elements. So basically different operations. So this is the result that represented in the paper, and all the baselines they are comparing here, mainly actually they compare with deep set. Those are the 3 baselines based on, it's actually derived from the architecture of this model. So either you have the hierarchical structure, then you don't have, then you actually flatten on the set, and then you use one layer, then you learn from the whole elements of the whole set. So either you explore the hierarchical structure, or you learn from all the elements. But all those are deep learning approaches. And you actually see in some of the cases, deep set perform very well. And this one is slightly lower, but in some other, like a little bit more complicated, like when you have to do the you find the intersection of the set, and you find the union of the set first, and then you do the operation on top of that. Then the proposed architectures tend to work better. This one is another result on the unique count and unique sum of the when you heavily relies on how accurate you can derive the intersection and union, then this actually perform much better than the other approach. So the second task that they perform is to compute the Aramic or ADA index. So this Aramic or ADA index is the similarity measurement on graph data. So you measure the similarity between 2 nodes in the graph. Let's say here you measure the similarity between node U and node V. NU and NV are the neighbors of node U and node V. And this actually gives you the degree of the node X. So you actually measure, so it's discount if you actually link to the neighbor, but it's too popular. Then this discount by the log function, log coefficient. So then the similarity between the 2 nodes actually based on their neighbors. They're weighted by their neighbors. So this actually exploit the hierarchical structure setup set in the sense that you have two sets, which is the two nodes, and then inside each node you have their neighbors. So in order to compute this one, you represent the data in the setup set format, and then you use the hash model, and then you can predict. And these two also use setup set architectures, and this one doesn't. So the result actually they measure the task is actually the regression task. So they measure the MAE then NFE, MSE to the correct index, and the results show that it has performed. I mean, I don't know like how actually like the arrow represent the significance, but this is how they show that it has actually performed better than the other approach. Another task that they try to conduct is the subgraph hyperlink predictions that I presented a bit earlier. So the hyperlink between the subgraph is that whether or not the two subgraph, there's only one link between them. So either one of the element of the two subgraph that connect it together, then we say that there's hyperlink between the two subgraph. So yeah, so essentially they hide a link and then they just try to, it's basically the link prediction, but it's not between node or node, but between two subgraph. So then in this particular case, we can actually exploit the hierarchical structure of the subgraph and then the element inside the subgraph. So, and actually, it's no surprise that these two methods exploit that hierarchical structure and actually tend to perform better than the other approach, and has actually performed better than this one because of the argument is based on the attention mechanism that they put on the top of the set representations and the setup set representation. The last part they want to compare is the point cloud classification. So point cloud data that I presented earlier come from the 3D sensors. So they do two tasks. First is anomaly detection, and this one is actually, so this is the example of how point cloud data represents. So this one we just actually show it in 2D, right? But in reality, each point, they're gonna have the coordinate in the 3D space. So let's say here they are given a set of all the point cloud, we're going so-called image. We can actually call point cloud image here. So let's say 5 image here, right? So 4 of them come from a chair object, but this one come from airplane. It's a bit hard, right? But this actually come from the airplane image, and this is an anomaly. So the task is that whether you given these 5 examples, then you have to predict whether there's an anomaly inside that set or not. Another task is that unique label counting. So unique label counting meaning that you actually have the set of different point clouds or different objects. So you count how many unique objects that appear inside the set. So this is setup set kind of data. And when they compare, they actually compare with the other baselines that we compared earlier. And in this particular task, it's heavily also again is actually heavily rely on how well you perform on the set operation first, and then you operate on the elements level. And then the hash architecture actually significantly outperform the other approach. So again, right, the anomaly detection task, right, random guess is 0.5. Because it's 50% chance that there's the way they conduct the data. So 50% chance that they're gonna have anomaly inside the set, the data. So this is they analyze when they actually the M here is how dense data is. So like how many points they're gonna use to represent the object. So the more point in that class, right, the image is easier to be classified. In this particular case, they when you actually increase the point, then the task become easier, then it's performed better. Then actually heads can actually do slightly better when you have more points. In this particular case, they analyze. So for the heads, right, this is to actually reduce the computational complexity. So for set, the number of elements actually vary, but in some cases you don't actually want to make use all of them. So you just fix like this time I only take like the first 50 because you have the permutation layer. So this time I take the first 50 points. Next time I take another 50 points. Next time I take another 50 points. Then in a sense, over time you actually learn the representation of an object, but you don't actually want to make use all of them because it's going to be the computational overhead. So that is all about the paper that I'm going to present today. So now it's a Q&A section.